Hi again. We're going to pick up where we left off with the Heisenberg uncertainty principle. I'm going to start with an example problem before we finish up the note sheet and look at Schrodinger's wave equation, which is extremely abstract, and we just have to kind of understand it and more in a conceptual and graphical nature. So the expression for the Heisenberg uncertainty principle in terms of momentum and position is expressed right there. And that the right-hand side says h bar over 2. H bar is just a convenient way of saying Planck's constant divided by 2 pi. But for our purposes, we're just going to stick with the simple h over 4 pi. Okay, so we're going to apply it to the problem, come back, like I said, and then finish up the notes. So let's turn to a problem here. These are your homework. You're going to do the rest of these on your own. I will post an answer sheet for these. So let's say we got a position of a proton has a certain mass is measured with an accuracy of plus or minus 10 to the negative 11th meters. Okay, so we're down to a picometer, and that can be done with various instruments. And so in order to see that, we are going to affect this momentum. So we could ask a very simple question: what's its uncertainty in momentum? And that would be pretty straightforward. So we would say delta x times delta p equals h over 4 pi. Therefore, the uncertainty in momentum is equal to h over 4 pi times 1 over delta x. And since delta x is really small, we expect our uncertainty in momentum, therefore, to be fairly large. So but h over 4 pi is an extremely small number. So if I take that, work out the math, let me just do that real quickly. See if I can do that. I get the uncertainty in momentum is on the order, well, I'll just do that, 5 times 10 to the negative 24th kilogram meters per second. Now that seems like a really, really small uncertainty, and it is. However, and this is where I find this more interesting, because the part A is kind of trivial, but how we can apply it is part B. What, therefore, is the uncertainty in the position 1 second later? Okay? So in other words, the act of observing the proton has sent it changing what it did. It changed its momentum essentially by that uncertainty amount, by at least that amount. And so we can use essentially kinematics. And so the key here is, how do we go from momentum to position? Well, we figure out how fast the electron is moving. So if we know that the velocity of a proton, is its momentum divided by its mass, then the uncertainty in the velocity is the uncertainty in the momentum divided by the mass. And then it follows that the uncertainty in the position, x, is simply going to be delta v times t. So I will let you work out that string of equations, but you will find that it is a surprisingly large value. Okay, for numbers 2, this talks about electrons in excited states. We haven't learned that physics, but you don't need to know it necessarily here. But the important thing is we're using the other complementary pair that we introduced. The relationship between uncertainty and energy state and the amount of time that it has that energy is also equal or greater than equal to h over 4 pi. So you're going to apply it there and there. And then we're bringing a little bit of de Broglie wavelength. Number 3 is more of a review problem than anything else. It's not necessarily tied into the uncertainty principle, even though ultimately the idea that matter can have wave-like properties lead to the uncertainty principle. Excuse me. And then number 4 is a diffraction problem, and I want us really to appreciate the connection between diffraction and how we can learn about the uncertainty principle from that way from a classical standpoint. Okay, so let's go back to the notes. So we understand now that we have to alter our view, at least as best we can conceptually, of what a electron is or a proton. So the best we've said is it's a matter wave. And since it has valid wave-like properties, we have to then basically come up with a new equation that describes how that matter wave moves through space and time. And if you're going to describe an equation of that particle wave as a function of time, we know the role that wavelength is, but we don't know, or we haven't really talked about, what role would the amplitude of that wave is, right? So if you're going to come up with a wave equation, that wave equation is going to have an inherent amplitude. Okay, but what does that mean? physically. Okay, so we're going to try to make an attempt at understanding that. Okay? And then this, again, comes out of the fact that you can't think of it as a hard sphere or particle. Let me just say particle. Okay, at the quantum level. Okay, because it has no exact location. Okay, so let me introduce you to Schrodinger's equation below before I fill in the blank above. Okay, so here is one version of the time-dependent Schrodinger's equation. Just look at that. Think of beauty, or perhaps to you it looks like a monstrosity. This is a differential equation. We will not have to solve it, and it can be exceedingly difficult to solve except for the simplest of situations. But let me try to point out the key things that we want to try to at least understand a little bit. We have here this part, which is it's a rate, right? We're seeing how something changes as a function of time. And this is our matter wave. And our matter wave is summed up with this function called psi, Greek letter psi. And I'll talk about that in a second. Interesting here, I, that's the imaginary number, so you can use imaginary numbers, and there's h bar. Over on the right-hand side, again, here is the psi function, and then the rest of this is electric, that's potential, that's a potential well. Okay, it has something to do with energy, and then this gradient sign is basically a fancy way of saying how it changes the slope of that. And that's very simplistic what I said there. So what we're ultimately trying to do in Schrodinger's equation is show how a particle wave or a matter wave changes with position r and time t. And it depends on the energy state of it as well as some other factors. So what we want to do is talk about this psi. So psi is really the key to this and what we want you to understand at the very simplistic level. Okay, so psi is in essence, or psi squared, is the amplitude of that matter wave. Now, if I want to describe an electron, I might come up with an equation, an application of Schrodinger's equation, and that function might give me something like this. Okay, that's the equivalent to the matter wave of that particle. And that matter wave has a wavelength and also has an amplitude. And that amplitude is, if you will, proportional to psi squared. Okay, so what exactly is that amplitude? That's what I've been trying to get to in this very convoluted way. So ultimately, what the amplitude, psi squared, is a measure of is the probability. And that's the heart of quantum mechanics, of finding a particle at a given position and time. Okay? And so think about that and how that fits in with the Heisenberg uncertainty principle. You have an electron in a particular situation. It could be just a free electron. It could be part of an atom or some other an electric field such that this aspect of the equation will vary. But how you want to understand how that electron changes with position and time, you can't use classical physics where you treat the electron as a, like I said, a hard little particle that has a specific position at a specific time with a specific momentum. The act of observing it, seeing it, makes it inherent uncertain what the position is going to be depending on how well you know the momentum and vice versa. So the best we can do is describe that particle as a wave function, a superposition of multiple states, and that probability is reflected as psi squared. When you measure it, then what happens, and this is the really weird thing, when you measure the particle, until you measure it, you really don't have any idea where it is, except that it's more probable here than it is there. But the act of measuring it then pinpoints what it is, and it makes that wave function collapse. So I'll show you some videos on it because it's a very odd idea, and I know I'm not doing a great job of it making sense right now. Okay? But let me just do a quick little example. So this is something that the AP would expect you to be able to do, and it's not overly difficult. You don't have to do any math. So let's say I represent wave function of two particles. Which particle is more likely to be at position X? So I have a wave function right here, that little wave packet that's generated by an application of Schrodinger's equation. Okay, so it's not just a simple monotone wave. if you will. Here's x naught, and then here is another wave packet here, a little bit more spread out in space. So if we're asked which is most likely, so that's a probability, what we want to understand that likeliness, that psi, is proportional to the amplitude. Technically it's psi squared, but that's not the square part really is an issue here. So it's not so much how localized that wave packet is, like this one, that seems to be more localized. What matters is the amplitude of that wave function. In other words, this one has a bigger amplitude. And since it has a bigger amplitude there, then the answer is this wave, this particle, as described by the wave function, is most likely to be at x naught. Okay? I would tend to, if I first looked at it, go with this one, because it seems to be more clustered around it. It's not, but this is not a precision type of problem. It is simply when we put in the values for the parameters of what the particle is doing, and we get that wave function as plotted on the graphs there, the one that's most likely there. It's most likely there where it has the highest amplitude. I know that's odd. Okay, so I want to finish up with a famous experiment. You might have heard of Schrodinger's cat experiment. Okay, and the idea is, and I believe Schrodinger came up with this mental experiment, is you put a cat in a box so you can't see inside it. And you have some random event here, and this could be a radioactive decay. So a radioactive decay is inherently random. You don't know when it's going to happen, but if it does happen, it sets off a chain of events where you can see this little hammer falls and it breaks a vial of poison and the cat is asphyxiated, poisoned. So the heart, and as cruel as that is nowadays, back then, I guess the physicists didn't hold cats in high regard as we do now. The inherent question is, until you look in the box, what state is the cat in? Is it dead or is it alive? That's a classical way of looking at it. In other words, you don't see what's happening until you open the box. And so until, let's say you put the cat in a box and you come back an hour later and say, is the cat dead or alive? From a physics standpoint, that's the wrong question. It's not, is the cat dead or alive? It's what state is it in until you observe it. And basically what quantum mechanics is telling us, via especially Schrodinger's equation, is until you observe it, until you open the box, the cat is in a superposition. Superposition is this fancy way of saying a bunch of different type of wave possibilities superimposed over each other. It's almost like an interference effect. It's in a superposition of two states, both dead and alive. Notice I didn't say or, I said and. So until you observe it, the equations that describe its probability of being one or the other means it's both at the same time. It's dead and alive until you open a box. And when you open a box, something happens that we're not quite sure how that mechanism works, where the wave function collapses into one particular state, dead or alive. But you don't know that until it happens, but the equations say it's in both states until you make that observation. And that's where quantum mechanics deviates perhaps most profoundly from classical physics, is that until you observe a particle, it is in all possible states. And then the act of measuring it, depending on your experiment, makes it collapse into one of those states. But you cannot know what that state is going to be until you measure it. And that's what troubled so many physicists, especially Einstein, who just refused to accept that conceptual way of looking at things. All right, so I have a bunch of links here. I will attach those separately. And once you look at those, maybe this will make a little sense. And then you can do the homework problems. All right, as always, you can always ask me questions, or maybe we'll wait till we meet again to discuss this.